All right, in this video, I'm going to recap the lesson on kinetics, reaction rates, rate laws. So, take a moment, pause this video, and see if you can analyze this reaction. Is the decomposition of nitrogen dioxide, which is a source of air pollution, and we're given this data, time versus the concentrations of these reactants and products, right? Time versus concentrations of these products and reactants, and see if you can come up with some sort of interpretation or analysis. One of the things you should realize or be able to see is that in this data, the concentration of the reactant is decreasing over time. As time goes on, there's less and less of the reactant, and that makes sense because those are the ingredients to this reaction that get used up to make more of the products. And conversely, the products, NO and O2, their concentrations are increasing, right, as the reactants are being used to make the products. That's logical. You should also notice something about the rate of appearance and the rate of disappearance, or the rate of rate that the reactants are being consumed versus the rate that the products are being produced. So go ahead, pause your video if you haven't tried that. Well, the thing to notice here is the rate of disappearance, right? The reactant is going to disappear. So this rate here, right, which is the concentration in molarity over seconds time. Okay, this is molarity. That rate is the same rate as NO, nitrogen monoxide, is appearing. All right, and again, that makes sense as well because notice the coefficients in this balanced equation tells us for every 2 molecules of NO2, we get 2 molecules of NO, or every 2 moles of NO2, we get 2 moles of NO, and you can interpret it those ways. But what about O2? Right, the rate is not the same, right? The rate is half, right? And that's, you're only producing half as much of O2 compared to NO because of the balance reaction. Okay, so notice this is roughly, half of the concentration of NO. All right, roughly half, straight down, if you compare the second and third columns. All right, so if we were to plot all this out into a graph of time versus concentration, go ahead, why don't you pause your video and give that a try. All right, so time versus concentration of, try all of these. Let's just call it X for now. All right, so I'll do this. I've been kind of mixing these colors up. I'll do the reactant, nitrogen dioxide in blue. All right, and what you'll see is it starts at time 0, right? And let's say this is that concentration there. That's the highest concentration. That's the beginning. That's how much we have in the beginning. All right, so put that in a more neutral color. All right, 0.0100 is, let's say it's right there. Okay. All right, so the concentration of that reactant is going to start right there, and as the reaction happens, it's going to kind of look something like that. All right, the slope is steep near the beginning, and then it tapers off. The rate becomes slower and slower, and that makes sense because this is not true for all reactions, but according to the collision theory, as there are less and less of the particles, there are less and less for them to collide, or in this case decompose. So the rate of the reaction is going to slow down as you progress through the reaction. Okay, so now if we draw the other ones, well, I'll do NO here in red. So that is going to have zero concentration, right? Zero concentration at time zero, which is the initial. Okay. And that's going to be formed at the same rate as the disappearance of nitrogen dioxide. And that makes sense because that is being used to make NO. NO2 is used to make NO. And it's the same mole ratio, right? So again, as time goes on, as there's fewer and fewer of the reactant, there's going to be a slowing down of the formation of NO as well, right? As indicated by the slope of this graph. Now O2, what would that look like? All right. So again, that's starting at zero. There's nothing there because the reaction hasn't started before time zero, or at time zero. It's also right there, but this time this one is being produced half. That's not drawn to scale. Let me try that again. Half, all right, roughly half of the formation of nitrogen monoxide, NO. All right, so the graph is going to look something like this. So those are the some of the key takeaways, and let's just recap some things from a previous lesson. Recall that the rate, we're talking about the change in concentration over time. So that's delta concentration of some reactant over the change in time. Oftentimes we start at zero, time zero, so it's usually just going to end up being the duration of whatever time increment that is. Let me just highlight a few things just to make this clearer. Right, so these delta symbols are Greek symbols. They're just final conditions minus initial, right? Or the second reading minus the first reading. Okay, and this here bracket means concentration. Right, and in this lesson, it's going to be about reactants, and then pretty much the only form of concentration we'll use, at least right now, is molarity. Right, and we'll use the symbol M, which is moles per unit volume. Most oftentimes it'll be moles per liter, for example, moles per liter, right? Which is going to be called molarity or molar concentration. Right, so why don't you use the, here's the equation again, so I don't have to keep scrolling up and down. Why don't you use this decomposition of nitrogen dioxide equation and write this rate expression, this for let's say the appearance for oxygen over the first 50. You know what? Let's use some data. I'm gonna just. All right. So take the data, and we often use the to get these data. We often use the initial the readings at the start of the reaction, and the reason is the more this reaction progresses to the right, in other words, the more products that are made, at some point they're going to react and turn back into the reactants, and things get really complicated then. And once you reach equilibrium, then you got both things going on, and we'll talk about more of that in a future lesson. But the point of this is these experimental data are we're looking at the initial time of the reaction, because things get complicated once we get more and more products. In any case, why don't we figure out what the rate of change, right? A rate of the change for oxygen, right? The rate of formation in the first 50 seconds, let's say. All right, so let me just copy this over, copy another one over. All right, I just copied that data table over here. All right, so we're looking at the rate of formation of O2. So what would that be within the first 50 seconds time increment? All right, so we can write that as, for O2, the change in the concentration of oxygen over the change in time. Okay, and so what we're going to get is, if we show our work, final minus initial, all right, 0.0011 minus 0 over 50 seconds. All right, this is molarity. All right, what you're going to get is, punch that in your calculator, you're going to get 2.2 times 10 to the negative 5 molar per second. And oftentimes we're going to rewrite that second in the numerator as seconds to the negative 1. Okay, so do the same thing for the rate of formation for NO within the first 50 seconds. All right, if you do that, you're going to notice that it should be twice the rate of formation of O2 because the coefficients indicate that. You're going to get twice as much NO as you do O2. All right, and if you punch these numbers in, you should get that. Now these numbers aren't exact, so the concentration, the rate that NO is being formed is the change in concentration over the change in time. Okay, and if you do that, you're going to do final minus initial, 0.0021 minus 0. These are molar, by the way. Label these. Over 50 seconds is a time increment. You could have broken that down too, as well as like 50 seconds minus 0 seconds, and you're going to get 50 seconds because the initial reading is 0 on all of these. All right, so punch that in your calculator, and you're going to get this about double that number. So it's going to be 4.2 times 10 to the negative 5 molar per second. All right, now try this last one without reaching for your calculator. All right, so try what is the rate of disappearance, or the rate that NO2 is being used up. Okay, and try to do this last one just intuitively based off of what you know about the rates of the products. Well, the rate is going to be the same as the rate of the formation of NO, because for every 2 of those, every 2 of NO2s, you get 2 of NOs, right? So the rate is going to be the scalar, or the absolute value is going to be the same, but the sign is going to be different. All right, so let's see. All right, so the change in concentration of the reactant, which is NO2, right, over the change in time is going to be, now this time the final number is less than the initial number, so you're going to end up with a negative number. It's going to be exactly the same quantity, just negative. Right? So it's going to be negative 4.2 times 10 to the negative 5. Looks like meters, huh? Molar per second. All right, so just kind of giving you a conceptual view of rates. So now we're going to take this and show you how to calculate or write rate laws. All right, so let's go over how to write rate laws. Important things to know is that rate laws are determined experimentally. All right, in the lab, like these data points are tabulated, and it's let me also write this. We express these rate laws at initial conditions. Right, and again, the reason is as reactions proceed and you get more and more products, they start at some point turning back into reactants. All right, and then that makes things really complicated. So as soon as you get a reaction starting in a test tube, beaker, or flask, or whatever, what have you, you want to get that rate as close to that initial point as possible. Okay, so for now we're going to rate these rate laws only dependent on the concentration of reactants because um, there are no products yet, or they're just starting to be made. Okay, so the format we're going to use is, let me pick a different color that stands out. So the rate law is going to have this format. The rate is going to equal, and this is a lowercase k. We're going to use a capital K in an upcoming lesson, so not to confuse that with lowercase k, and the concentration of the reactant A, let's say raised to some power x, times the concentration of another reactant. If we have two reactants, let's call that B, raised to some power y. Okay, so I'm going to label some of these things here. This K is known as what's called a proportionality constant. It's experimentally determined, and there's a K value for every reaction at different temperatures, and it's just a huge tabulated data thing, and so it just keeps everything in check, proportional to each other. So that's just a constant, and that's going to be different for every reaction. Now these powers are known as orders. Okay, so they're the powers or the orders of each reactant. So you would say this is the order with respect to A, and Y is the order with respect to reactant B, and so on. Now, you can have, of course, you can have more than two reactants, then you would just go, concentration of C to the power of, or raised to the, with the order of Z, and so on. And you can have certainly one reactant, which would just the case we just had at the beginning of the video, the decomposition of NO2. All right, and actually, if we were to write the rate law for that example, it would look like this. All right, K, concentration of the reactant, is NO2, that's the only reactant, raised to some power x, or with the order of x. Okay, and these are, again, experimentally determined. But we're gonna show you how to write this expression fully with the experimental data given to you, which is exactly what we're going to ask you to do on your test. All right, so let's go over some of these examples. All right, so I just in our first example, example 1, let's call this. All right. Example 1, we have this reaction of NO plus Cl, chlorine gas plus nitrogen monoxide gas, leading to NOCl. And we're given experimental data here, trial 1 or experiment 1, trial 2, trial 3, and we're given the concentrations. And these are all initial concentrations and initial rates. Right? These are all initial datas. So as soon as this reaction starts, we're telling you the concentrations. All right, we're doing 3 separate experiments, and so all right, let me back up here. So you go into the lab, you grab a test tube, you put 0.1 molar of NO, and then you grab another test tube and you put 0.1 molar of Cl. Well, maybe not test tubes. These, all right. Well, these are gases, just in some kind of container, okay? And then the moment you put those two together, they're going to start to react, and then you're going to calculate the rate of disappearance or the speed of the reaction right there. Okay, how fast is the speed happening? Okay, so now, given this information, we are going to write the rate law, which is again in this format. In this case, it's going to be the concentration of NO raised to some power x times the concentration of chlorine is the other reactant, so raised to the order of y. All right, we're going to figure out K, X, and Y, and that's what we're going to ask you to do on your test, given experimental data like this. All right, and the key here is you want to pick two trials where the reactant that you're solving for. So let's just solve for the order with respect to NO. Let's do that first. So in order to find X, in this case, right there, X, we want to look at two trials where NO is changing, but nothing else is changing. All right, when I mean nothing else, it's chlorine in this case. All right, so what two trials is NO changing, but chlorine is not? Well, if you say, look at trial 1 and 2, I'm sorry, 1 and 3, right? NO is changing, right? It's changing, but so is chlorine. So this is not the trial you want to pick. It won't give us any useful information because whatever the rate of change is, you don't know if it's because of the change in NO or the change in Cl2. So you want to pick a trial. Now, 1 and 2 is also not good because that shows you no change in NO. All right, so hopefully you've seen now is you want to compare trials 2 and trials 3. Okay, so I'm gonna try to color code this actually. All right, so for that maroon color, NO, we're going to compare trials 2 and 3. So what just happened between trials 2 and 3? How much the concentration change? All right, between trials 2 and 3, we doubled it. So in trial 3, we put twice as much of this stuff in a test tube versus our second experiment. So this is a 2 times increase. Okay, so we're going to put that right underneath here. Let's just put it right underneath. All right, so it increased by 2. Let me line that up a little better. All right, we're looking for the rate, okay? Oh, actually, we have the rate, sorry. So the rate increased by what between those two trials? This one's maybe not the easiest thing to see, but if you divide the bigger number by the small number, it goes in 4 times. So the rate increased 4-fold. All right, so now you can solve for X. All right, now these are on our test. These will always be whole numbers. All right, but in a lab, you can imagine these are not going to be pretty numbers. They'll be fractions or decimals, and you'll have to pull out your calculator and use logarithmic calculations, which maybe if we have time we'll get into. But all the problems on your test will look something like this, where you'll be able to just do it mentally. All right, so 2 raised to what power will give you 4? All right, so then this here is going to be what we call a second order with respect to NO. All right, so let's pause your video and try to find the Y value or the order with respect to chlorine. Okay, so we'll do chlorine in let's use orange here. All right, so what 2 trials are you going to look at? Well, you're going to look at trials 1 and 2. Now again, 1 and 2 because chlorine is changing and the other reactant is not. Okay, so that is also a 2-fold increase. I'm just going to go down right here and do that one. All right, so 2-fold increase. Now, what about the? Let me go back and label this here as well. That's a 4-fold increase. So this is also a 2-fold increase. The rate. Okay, so the rate also had a 2-fold increase. All right. So 2 to what power will give you 2? All right. So 2 to 1 power, the power of 1. So Y is going to be 1, and you can read that as a first order reaction or first order with respect to chlorine. Now to get the total overall rate of reaction, the rate order, you would add up all the individual orders. So 2 plus 1, the overall would be 2 plus 1 is 3. All right, let's do another. Actually, let's solve for K now. All right, so in order to solve for K, let me rewrite this actually, so it's a little bit cleaner. All right, got K, concentration of NO. What did we say that was? 2. It's a second order reactant, and chlorine first order. We don't write one, so you're probably not going to see that one there. But we'll keep it there for now for visual purposes. Now we can solve for K is the final thing we need to do. And in order to solve for K, we're just going to use a little bit of algebra. Right? You can pick any trial. Pick the trial that has the simplest numbers to work with. I'm just going to use trial 1 because there's ones in there. Right? Zeros are my favorite number, and then ones are my second favorite number. So I'm going to use that. And you would get the same answer no matter which trial you picked. All right, so the rate here is for trial 1 is 0.18. Okay, don't forget that the units can get a little tricky here, so don't be careful with them. All right, moles, molar per second. All right, equal to K is what we're looking for. All right, the concentration of NO is 0.1 molar squared times the concentration of chlorine is 0.1 molar to the 1, which is just itself. All right, so we could have rearranged this before. All right, but let's isolate K by dividing both sides by everything else. All right, these are going to cancel out. And if you punch that in your calculator, now be careful with the units. Okay, you're going to see one of the molars are going to cancel out, but this one is not. All right, so punch those numbers in. And you should get K is equal to 180 per molar per second. All right, I'm just going to bring the seconds to the top. So that is the value of K. I'm not going to circle that yet. And let's plug that back into our rate law. Ran out of room. Okay, made some more room. All right, so our final rate, jeepers. All right, so our final rate law is going to be 180 molar to the -2 seconds to the -1. Concentration of NO is second order. Chlorine gas is first order. And so there is our final answer. That is a rate law for this this combination or synthesis reaction of NO and Cl2. All right. I think we're going to stop here. This video is reaching 30 minutes already. I'm going to do several more worked out problems just the same way as this one is also the same way you're going to see on our test. So how to write rate laws given experimental data, and also calculating the value of the rate constant